So as we mentioned in the previous video, the Robinson annulation is a way to make a ring, to create a ring, which is very biologically useful because rings fit reliably into receptor sites. So it's a way to create a ring by doing first a Michael addition and second an aldol condensation. Now, the sort of key feature you'd want to see in a molecule that would remind you of the Robinson annulation is an alpha-beta unsaturated ketone, an alpha-beta unsaturated ketone in a ring. If you see that feature, so here you have the alpha carbon, the beta carbon, you have a pi bond, a degree of unsaturation in between them. If you see an alpha-beta unsaturation in a ring, break it apart. You can form that alpha-beta unsaturation by doing an aldol condensation. And we did some exercises, videos and exercises previously in this homework set, where we thought of the two products, the two reactants you'd need in order to make these alpha-beta unsaturated ketones. And what you'd need, I'm going to redraw this molecule. What you would need is this alpha carbon as a nucleophile, and you need an electrophile for it to attack where it forms the other bond. So you would put a carbonyl there. And so that, by having these two features, you can add a base, and that will turn this into a nucleophile, and that would attack the electrophile of this carbonyl next door. So whenever you see an alpha-beta unsaturation in a ring, redraw the molecule but without the double bond there. And on the end of the double bond that didn't have a carbonyl, draw a carbonyl in. So you can do an aldol condensation with those two. That's the first sort of step. Once you have that, you'll see another feature that will give you information about how to do the Michael addition. Because after you draw that other carbonyl in, you will notice an alpha carbon that is alpha to 2 carbonyls. And that is the sign of a Michael donor, a weak nucleophile that can attack a beta unsaturated compound. So, for example, if we took this right here, let's draw that out. We have that one carbon here, and we have another carbon with an aldehyde to the right of it, and another carbon with an aldehyde to the left of it. We also have a methyl group here. So that is this molecule here. And you'll notice that now that it's drawn out clearly, you can see that this carbon here is alpha to both of those carbonyls. And so if you treat it with a base, you can form a lone pair with a full negative charge. That lone pair will be stabilized over all 5 of these atoms. It'll be spread out over all 5 of those atoms and stabilized. So it'll be a weak nucleophile and will attack the beta carbon of an alpha-beta unsaturated aldehyde or ketone, which you can see we can form here. So if you take that purple side of the molecule, you have the ketone, you can have an alpha-beta unsaturation. And if you have that, then this beta carbon will be slightly positive. Now, the carbonyl carbon is there, the alpha carbon is next door, the beta carbon is one further away. So that's an electrophile. The Michael donor can attack that, this Michael acceptor, to attach, to create this new carbon-to-carbon bond. And so those are really the two pieces that we would need. We would have this original molecule, and we would want to react it with this alpha-beta unsaturated molecule. And if we treated those two with sodium hydroxide and heat. The same very simple recipe that we saw in the previous exercise where we drew the mechanism for the Robinson annulation. Then the two reactions happen. The Michael addition happens, followed by the aldol condensation. So the Michael addition will have this alpha carbon attack that beta carbon. It'll give you this product here. The hydroxide will steal an alpha hydrogen from this other alpha carbon, and that will attack the carbonyl carbon and form the second ring. And with heat, you'll do the elimination that creates the alpha-beta unsaturation. So this is a very cumulative, complex problem. If you were able to follow along with this analysis, that's really impressive. That's really awesome. I wanted to give this to you for those of you who are interested, for those of you who may do biochemical research in the future, so that you would have been exposed to this and can see this very powerful combination of first a Michael addition to give you this, and then an aldol condensation to give you the final product to create this ring. But I wouldn't put a synthesis involving the Robinson annulation on a test for this chapter, for this class specifically per se. So this is in a sort of enrichment exercise to help you ease into future classes and more complex research problems. But if you're having trouble following this reasoning pattern, that's understandable, and don't feel too stressed about that. But if it doesn't make sense, I would encourage, and you want to understand it, definitely reach out to me. I'd be more than happy to explain it in person, and then also in more detail in person, or if you have any questions, specific questions, I'd be happy to answer those in person. And another tack that you might take is to review the Michael additions, and then review the aldol condensations, and then come back to this and see if it makes a little bit more sense.